Hello everyone, I'm Dengyu from OurMesh. My talk today is Run uZFS in Rust Async Runtime. Let me introduce myself first. I've been working on distributed storage system and started developing libuZFS last year. This is today's outline. I will first introduce libuZFS and Rust Async basics, and then talk about how we run libuZFS in Rust Async Runtime. In 2022, we brought ZFS into user space based on libzpool and Fuse. On the left-hand side is ZFS architecture, which includes ZPL, ZVO, and DMU. On the right-hand side is uZFS architecture, which utilizes the framework of ZDB and libzpool to run ZFS in user space. Recently, we took a step further and brought libuZFS based on uZFS. The motivation is in two ways. First, we want to turn ZFS into a storage engine for user space file system. Because ZFS has many nice features such as copy on write and snapshots. When developing a new user space file system, we aim to build upon the existing features of ZFS. Secondly, Rust has become more and more popular because of its strict compilation check for memory and concurrency. Rust also has many useful features such as async await and its compatibility with C. So we wanted to combine Rust and ZFS. This is the architecture of libuZFS. On the top, we implemented libuZFS, which works similarly to ZPL. libuZFS provides some basic file system semantics based on interfaces of DMU. On the bottom, we developed VDEV file to replace VDEV file. It uses libAIO to maximize disk throughput. Interfaces of libuZFS are divided into three parts. The first is about dataset and how to manage it. It includes init, dataset init, and dataset close. The second is Anode operations, which stores metadata like attributes, the entries. We can use get_attr, set_attr, or create_delete to operate on the anode. The third is object, which stores file data. And the object can be accessed by read object and write object. Then let me introduce a use case by a read example. If we are developing a network file system, after receiving a read request, the network thread will spawn a read task to the worker thread. If this read gets cache miss, the worker thread will submit a ZIO to the AIO thread and wait for its completion. When the ZIO is done, the AIO thread wakes up the worker thread so it can continue running. In this example, the worker thread is blocked until ZIO wait returns. In this thread model, all tasks can only be executed one by one. So we need some way to tell the worker thread to switch to another task when our functions need to pause. Also, libuZFS has too many background threads. In a 16-way CPU VM, libuZFS would create over 200 threads per pool for task queues. In kernel ZFS, those threads are cheap, but when we are running ZFS in user space, the cost cannot be ignored. Before talking about solutions, let me introduce Rust Async first, and then use knowledge of Rust Async to solve these problems. The simplest idea for concurrent programming is thread per task. Our example is to read some data from the device and then process it. If we want to increase throughput of this model, we need to add more threads. If we have much more threads than CPUs, then CPUs will spend too much time on thread switch. To address the problem, we can use asynchronous I/O. This model can give us high performance, but the cost is scattered code logic. In this example, one task needs to be splitted into two functions, one for IO submit, the other for data process. If we want to do more IO requests in one task, we need to split the task into many pieces. Then we even need to register callbacks in the callback function. This makes our code hard to understand. Now that thread per task model gives us sequential logic, the only problem is the high context switch cost of thread. So we can replace threads with stackful coroutines. The coroutine switch also needs to switch stacks and jump to another execution flow using jump instruction. But the difference is that coroutine switch does not need to trap into the kernel. This difference eliminates the most significant part of thread switch cost. Furthermore, stackful coroutines uses stacks to save context. What if we save the context using state machine? In Rust, if we use $await behind the blocking functions, the outer function can be compiled into state machine on the right. In my function, we will first call the pull function of the read, which registers read request and checks whether the read is completed. If the read is not completed, my function will return pending to the worker thread. This return statement works like context switch in stackful coroutine because it returns control to the worker thread. After the read is completed, this task will be waken up. Well, when we want to resume the task, we first check its state, and the state is read. Since the state is read, we should continue work we left. And then the read is processed, and we can set the state to the right. Then we can execute the write future like the read. In last slide, we saw read future and write future. They are structures that implement the future trait. They have pull functions to make progress on execution. When the pull function returns ready, this means that the task is done. And when it returns pending because of some event, the worker thread can continue executing other tasks. After this event is ready, the task can be executed again, just from where where it pauses. Return to our problems. For the first problem that tasks can only be executed one by one. To solve this, we can implement libuzFS functions as a feature. When a function needs to pause, the pull method will return pending. After fixing the first problem, we can replace our background threads with coroutines. This reduces thread switch overhead dramatically. Next, I will talk about some possible solutions and the advantages of our chosen solution, coroutine feature. The first solution is to rewrite uZFS functions. We will rewrite functions as features manually, like what the Rust compiler does to async functions, such that we can call it as async function in Rust. This solution gives us high performance and low memory cost because it doesn't need no extra stacks. But it also needs a huge amount of rewrite work because all functions that may block need to be rewritten. For example, if we have functions A, B, and C, the function A is blocking, the function B will call function A, and the function C calls function B. In this situation, we need to rewrite all three functions because all of them, when we call any of them, they might block the thread. The second idea is to spawn a stackful coroutine to run C code. Then the Rust task can call notify.await to switch to another task. When the coroutine is finished, the Rust task can continue. In example shown by the figure, in the first execution of task 1 in Rust thread, it will spawn a stackful coroutine to the coroutine thread. Then the Rust thread can continue executing other tasks. When coroutine 1 is finished, it notifies the Rust thread to continue task 1. The advantages of this solution is that we don't need too much modifications. We only need to rewrite those logs or CVs and other system calls that may block the thread. We don't need to rewrite all functions that calls them. But the disadvantage is that every call needs at least 2 thread switches to finish, even for non-blocking calls. In our example, the task 1 will first be executed on the Rust thread, and then part of it must be run on the coroutine thread. After the coroutine is finished, we need to execute the remaining code on the Rust thread. So can we combine stackful coroutine with the Rust feature? If we do that, we got coroutine feature. In this solution, C functions continue to run inside stackful coroutines to minimize code modifications. And the coroutine is designed to implement the feature trait. So we can pull the coroutine feature on the Rust thread. If the target function is non-blocking, our first pull of the coroutine feature will return ready. Then we can do others. Then the task is done. We don't have to change to any thread. This is the simplified pull function of our coroutine feature. It works as follows. In the pull function, it will first call jump f context, which saves current context and jumps to the target function. When the target function pauses or finishes, execution flow will jump back with the coroutine state set. And then the pull method can return based on the coroutine state. If the coroutine is pending, then the method returns pending. If the coroutine is done, this method can return ready. This slide shows an example of using coroutine feature. The usage is in three parts. The first is the interface for external caller. The second is arguments for external C function. To run the function, we need to create a coroutine feature and pass arguments and Rust function to it. The Rust external C function will call a C function lib uZFS object read. This function is implemented in C and exported to Rust through bindgen. After doing all of this, we can run C code in coroutines context. Also, to detect pending state caused by conditional variables or mutexes, we need to re-implement synchronization semantics. We implement a coroutine futex, which has similar semantics with the kernel futex. It also has wait until, week 1, and week all. Then let me show you an example of task execution by using ZL wait example. The pending point of ZL wait is CV timed wait of our CV. Since we have re-implemented conditional variable, so when we want to wait on the RCV, we will first mark the current coroutine as pending and jump back to the pull function of the coroutine feature. Then the worker thread can execute other tasks. Our first task is ZL wait for ZL1. In this task, we will first call wdev our start to submit a ZL to the AL thread. Then it will call CV timed wait. In this function, it will add this task in the wait list of the LCV. And then the execution flow will jump back to Rust pull function. So the executor can execute other tasks. Before the L wait for the L1 is done, the thread can continue executing the CPU task. After the CPU task, we can execute ZL wait for ZL1, for ZL2, sorry. ZL2 task works the same as ZL1 task. It will add itself into the wait list of LCV2. In this state, ZL1 task and ZL2 task are both waiting on its LCV. When the L request of ZL is done, the AL thread will call ZL done. In ZL done, it will first remove ZL1 task from the waitlist and add the task into the run queue. Then the execute can execute ZL wait for ZL1 from where we suspended last time. So when the L request of ZL2 is done, it works the same as for ZL2. Since we have separate stacks, the Rust stack and the C stack, so GDB if we do nothing, GDB cannot backtrace from the C function to the Rust function. To resolve this, we need to set the C frame, the frame pointer of the C in the C frame to connect to the Rust frame. In this example, frame 0 to 3 are in C stack, the coroutine stack. Frame 4, 5, 6 are in Rust stack. We have also conducted benchmarks of coroutine implementation and pthread implementation. Because our depth of pthread version is limited by thread count, it achieves lower throughput than the coroutine version. And in other benchmarks like async write and metadata operations, the performance of both implementations is nearly identical. My talk is finished. Thanks for listening, and I'm ready for questions online.
Okay. Questions for Dengyu about ZFS and Rust async stuff? Yeah, go ahead, Alan. So when connecting the existing C code to the Rust code, did you find any bugs in the C code?
Yes, I have found one. When we do a read after a write in some situation, but the details is hard to explain here. The situation is that when I write some data and then I do a read, and the read may return all zero data. Yes, I have found this the problem yet.
Other questions? So, go ahead, Paul.
So I was wondering how is the Rust code that you did, is it like living in a separate repository from the ZFS code, or did you integrate it into the ZFS code base?
Yes, the Rust code is in a separate repository, and in the slide I have shown the link in GitHub.
Yeah, I think there's there's the link to the modifications that you needed to do to connect it together. Yeah.
Does that GitHub also include like the work you did for the you mentioned there's a like VDev AIO VDev type now? Is that also included in that GitHub, or is that separate?
We now have two repo. One is the Rust code, and the other is ZFS code we have modified. The ZFS code is in another repository, and you mentioned the VDev AIO file that is in the ZFS repo.
So while you were talking, I was also kind of like spelunking your code online. Great job. One thing that I didn't have time to look into, but I'm curious, if you build your code that way was, did you kind of like add all these new infrastructure as like a different kind of like target, like how we have different OSs like Linux, FreeBSD? You added this kind of like userland differences as an extra thing, or did you just, build on top of libzpool and just like don't care if the other things compile?
Sorry, I didn't get it. I didn't get your question.
The question is about like the basic, like how did you treat this target? Like there's Linux, there's FreeBSD, there's the userland, and like libzpool, and then there's what you did, right? And how does like what you did like integrate with those other things, or does it not? Is that paraphrasing?
Yes.
Yeah.
Our build is on the DMU layer, so we haven't based on DMU we build uZFS. This is this is not about this is different from Linux, but now we only support Linux for now. But I think it's different from the ZPL in kernel ZFS.
I think
Yeah,
that
I
answers
made
the
it.
question.
Yeah, I think maybe your question is also getting at like for like you must have changed, like you changed like mutex enter and CV, CV timed wait and sleep, like all these kernel functions that have already been abstracted out in the ZFS code base. So they do different things on Linux, on FreeBSD, on POSIX, userland, and now they have to do something different for Rust, like when you're running on the Rust async runtime. And I think you're asking like how it sits alongside those other three implementations.
Yeah,
right?
exactly.
Like, did you just change the POSIX implementation to be like, oh, there's no POSIX wait, like there's no POSIX sleep anymore, there's only Rust sleep? Or is it like some new file that has the Rust implementation?
Yes. For example, we have rewrite the implementation of the mutex. After our version of mutex, when we use pthread, the pthread lock may block the thread, and the coroutine mutex will only block the coroutine and switch it. Tell the scheduler to switch to another. Is this your wanting?
No, I think my question was indirectly kind of like answered.
Okay.
Yeah. So, yeah. Thank you.
Other questions? Cool. I think that this work is really interesting. I know it's not necessarily applicable to everyone here. Obviously, we're not all trying to integrate ZFS with like a Rust runtime. But I thought that it was really interesting how, Dengyu, you've taken advantage of the fact that like ZFS works on all these different platforms, and we've already abstracted out like everything that you could possibly need, like mutexes and CVs and, waits and sleeps and all these things so that it can work on, Linux and FreeBSD and in userland. And now you've kind of added a new backend for it, which, I think is really neat. I was thinking about how this might be applicable to other, like, Rust projects in general, like interoperation between Rust and C. And, I think it might be, but what's kind of unique is that with ZFS, we already have this giant C code base that's already abstracted out all these like super low level interfaces that you needed to replace for, to make it work in this different runtime. So I think it's a really neat application of the code base that we've created and how we've abstracted it out, and then integrating with this like newfangled, like very, compared to like threads, it's a very newfangled runtime environment that you never would have really thought that ZFS could work in. So I think it's really neat and look forward to seeing what you guys do with it in the future. Thanks a lot.
Thank you.